a lot of non-pure mathematicians, aka what we call applied mathematicians in this class, have been asking, how do we use all this linear algebra? Where do we use it in computer programming? How does it work in the real world? And honestly, like, one of the hardest things about teaching math, especially such an introductory course, is trying to convince you all as likely STEM majors or math enthusiasts that you're going to use this theory extensively in the future or in very niche applications in your respective fields. And I don't have a bazillion examples at my fingertips. But I do have an interesting one for another application of eigenvalues and eigenvectors that's less theory and actually more practicality. So rejoice if you are into the applied side of mathematics. Last video we covered diagonalization, which is more theory-based. There are actual real applications for why we want to diagonalize matrices. It's a very powerful tool in linear algebra, but this topic of Markov chains, if you've never heard of it, is it's pretty easy to grasp, and it's a really nifty application used in economics, used in statistics, and so we're going to just take a quick look at it, and then that's going to be the class. So, just as a very quick definition, a Markov chain is what we call a sequence of these things called probability vectors, and I'm going to define what those are too. Probability vectors. And I guess I should underline a Markov chain because that's what we're really defining here, is a sequence of probability vectors, x sub 0, x sub 1, ... all the way to wherever we stop, together with this thing called a stochastic matrix. Stochastic matrix P, such that, so the way it works is you take x naught and you apply this matrix to it, and out pops a new, what we call, probability vector. And I'm going to explain what this means, but loosely what it is, a probability vector. I guess I'll just talk about it since I'm here. So a probability vector it's a vector. So it is a vector with non-negative entries. So non-negative entries. And that all add up to 1. That all add up, I already wrote that, to 1. And that's what's called a probability vector. Now, as you can imagine, if I have a vector like 0.6 and 0.4, this could represent that there's a 60% chance of going one way and a 40% chance of something else happening. That's kind of what we mean by probability vector. And so, of course, to be an actual useful probability vector, we wanted the column to add up to 1, because otherwise this is kind of useless, right? Because otherwise, if you don't add up to 100%, then you're missing some data somewhere. And so the idea here being that if we take this, what we call our initial this initial vector here, or just a state vector or a starting vector or starting probability vector, there's 1,000 different ways you could say it. But this first, probability of something happening, and we run it through this thing which we call a stochastic matrix. And so the stochastic matrix P is a matrix whose columns consist of probability vectors. Okay. And so what this might look like, just to, I was planning on doing this in a completely different fashion, but since I wing everything that I do in this class, believe it or not, we're going to make a matrix, and I'm going to just kind of create a stochastic matrix for you all to follow. So let's make one that's 0.95 here, 0.03, 0.05, and then 0.15. 0.97. Okay, so this first column is going to represent some, let's just some probability vector v1. This is going to be some probability vector v2. And what this is going to represent is it's going to represent the likelihood that someone moves from either the city or the suburb, and they either move to, so if you're in the city, you might just stay in the city, but you might move to the suburb, and if you're in the suburb, you might move to the city. So how do you interpret this thing? What it basically says is that, at any given time, if you give me some probabilities or some distribution of the population, 95% of the people who are from the city are going to stay in the city, and 5% of them are going to be moving to the suburbs. And likewise, if they're from the suburbs, there's a very low chance that they're going to move to the city because you like the suburbs, and that's kind of reflected in the fact that 97% of those people who started in the suburbs are going to stay in the suburbs. So you'll notice that these columns add up to 1, which is very important. So that's what we mean when we say this stochastic matrix P. It's a very fancy word, and that the columns consist of these probability vectors. So back to the thing I was actually trying to define, which is what is a Markov chain. The idea here is that, if I give you that there's a distribution of the population, right, given by x naught is equal to 0.6 and 0.4 here. Okay, so what this says here is that 60% of our population currently lives in the city, and 40% of our population currently lives in the suburbs. You can go out, you can survey this, you can use statistical techniques to figure something like this out. And so what this is someone has created a model. Someone has created this stochastic matrix for you that basically estimates, where would people end up, right? If there's 5 billion people, how are they going to be split up, based on where they live? And so the idea is that we take x naught, we take this particular distribution of the population. It is also itself a probability vector, and we basically apply the stochastic matrix to it, right? We use our ingenuity and the data that we have collected to try and form this matrix in the first place. And it gives us a new distribution, right? So x1 is the new distribution of the population based on the workings of this stochastic matrix. So in this particular case, we could just do this really quick. 0.95, 0.05. We'll pop in the stochastic matrix here, and we're going to see what it does to our population distribution that has 60% in the city and 40% in the suburbs. So let's do some math, and we have some not so fun decimals here. So I'm probably going to need a calculator, and yes, you can use a calculator for this because these calculations aren't very fun to do by hand. But I believe that if we do this, we're going to get 0.582. I think that one I can do, 0.582. And then the next one, row times column again, we're going to get 0.418. And I want you to, kind of notice that, again, this is also itself a probability vector. It adds up to 1, and it is a new probability vector. So this, might be the distribution if this stochastic matrix represents these connections of probabilities, and maybe it's annually. So after 1 year, this is the expected distribution of population. And maybe we do it again, right? So where it gets the name Markov chain is that you take x1 and you apply the stochastic matrix to it, and you get out x2, and then you can do x2, and you can apply that and figure out in year 3, what's the distribution then. And you can use this to do city planning and budget planning and a whole bunch of stuff. And usually these stochastic matrices are created using math modeling and just collecting data, historical data and trends and things of that nature. So, calculating this, if you're given a stochastic matrix, and you're given, one of these distributions to start with, it's pretty straightforward to talk about Markov chains. And so, I mentioned, that, eigenvalues and eigenvectors were going to make an appearance. And, a natural question to ask with something like this is if this stochastic matrix here is modeling, what like kind of the trends that we are seeing in the short term, historical term, whatever. A very natural thing to ask is like, look, if I continue this Markov chain forever and ever and ever, to where I've done this n times, and I let n go to infinity, right? Basically, a very natural question is, well, what happens to our starting, our initial distribution in the long run, right? In the long run. Okay, what happens? And if you think about what that means, what we're essentially trying to solve here at this point is like we have a stochastic matrix, and at some point, if we do this for long enough, there's going to be some vector, and I'm just going to call it x this time. And we're going to have done this so many times that we have achieved kind of this equilibrium of sorts, that we have achieved where people are no longer moving, that the populations have balanced, the dust has settled, and we have achieved this result. Now, being guaranteed that we can do this, right? Because a lot of things with linear algebra, you got to be careful that you can actually do this. I'll prove to you that this is actually something that can happen. So, a question is, can px equals x even happen? Which basically begs the question, is lambda equals 1? In order for this to happen, lambda equals 1 always has to be an eigenvalue of a stochastic matrix, of a stochastic matrix P. Okay, so the question is, is this always true? And it turns out that it is. And so one way that we can do this is we're going to require something that you're going to prove in your homework, but I will write the result here, which is that the matrix P and PT, or this works for any matrices, but a matrix and its transpose have the same eigenvalues. Okay, so this is a theorem that you're going to prove. So theorem proved in homework. It's 5.2 number 20. Takes not very long to prove it. But the point is that what we're going to do in order to answer this question here, right, is what I want you to do is I want you to consider the transpose of this stochastic matrix P. Okay? And then, so then, look at P, the transpose multiplied by this vector that I'm going to say consists entirely of the number 1. So it's going to be a column vector that matches the appropriate size of P. So if P is an n by n stochastic matrix, then this is an n by 1 column vector. And the reason why I'm doing this is because the property of being a stochastic matrix, the big thing is that all the columns add to 1, right? That's the idea. So if I consider the transpose of this, then what result are we going to have? Well, if it's a transpose, then all the rows add to 1, right? And so if we look at like what, this random vector that I've said, hey, let's take this thing and multiply it by the transpose, what does that give us? Well, the effect that this has, remember that P of T, or P transpose, consists of a bunch of numbers. They're all decimals, or maybe maybe we have a whole number 1 and the rest are zeros or something, but let's just consider, the first row here, which is going to consist of a bunch of numbers, right, dot, 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 that all add up to 1. And so what effect does taking this transpose matrix and multiplying it by this random vector that I just pulled out of thin air here, what effect does this do? Well, that means that multiplying all of these things by 1 and then adding them, well, if I multiply all of these numbers by 1, I'm just going to get the same numbers. So multiplying by this column vector 1, 1, 1, 1, 1, 1, 1, etc. has the effect of just adding the values of this row together. But we already know that those rows add up to 1, so that means that my first entry here is going to be 1. And then if I take the second row and I multiply by this column, because that row also adds up to 1, I'm going to get 1, and I'm going to repeat this process, and I'm going to get out the exact same vector. And so what we've just done is we now here say, so this implies that for the matrix, for the transpose of a stochastic matrix, lambda equals 1 is always an eigenvalue, because the vector that I just pulled out of thin air, 1 dot 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 1, is always an eigenvector. Right, for any transpose stochastic matrix. And so because we have this, because there could be other eigenvectors associated with lambda equals 1, we don't know, right? It's not just that you get 1, right? We could have multiplicity, and so there could be more, but we're always guaranteed that lambda equals 1 will work. And based on the homework problem that you're going to solve, this little theorem here, these have the same, I wrote theorems because I'm just lost in my work, have the same eigenvalues. I'm sure that I said that. They have the same eigenvalues. And so this kind of inherently gives us that we're guaranteed that lambda equals 1 will always be a solution. And thus, so what does this mean? This means that we will always be able to solve this equation px equals x for lambda equals 1. So, taking a deep breath at this point, what this basically means is that if we go back to like this stochastic matrix that I brought up for this application, I said this is something that models how people are moving around in a city to suburbs and vice versa, if they are and if they aren't. If we start here and I ask the question, okay, in the long run, right, what, as n approaches infinity, what will the population distribution be? What will the population distribution be, right? And so that's like the question that we're asking, right? What's the population distribution going to be? And so we call, earlier we said that this question here always has a solution. It turns out that the particular vector here, we usually call this vector q actually. So I'm going to write that down here. So the vector q, or it's called q in your textbook, such that p times q is just equal to the q vector, is called the steady state vector, or we also call it sometimes an equilibrium vector, if I could spell, equilibrium vector for P. Okay, and so the steady state vector, is something that we're very interested in finding with systems. So if we kind of stick to this example that we were doing earlier, so for example, you might be asked to, like I said earlier, I'm just actually going to copy and paste this. So as n basically increases to infinity, as n increases to infinity, what will the population distribution be? And so remember that we're solving for this stochastic matrix that has 0.95, 0.05, 0.03, and 0.97, and we're trying to solve this. And so we're going to use the techniques that we've learned about with eigenvalues and eigenvectors. And so we're going to set up, of course, that our AQ minus lambda Q is equal to 0. And because our lambda here is just 1, we're going to get the setup where we have negative 0.05, we're going to have a positive 0.03, we're going to have a 0.05, and then a negative 0.03 right here, and then 0, 0, right? And so we're going to get here, so at this point, what do we get? So we're going to try and RAF this sucker. I'm going to multiply, well, okay, so I can see very quickly that the second row is just a combination of the first, so maybe I'll write that down, but I could also multiply the first row by 100, or maybe negative 100 would be more appropriate to get to the point where I have 5, negative 3, 0, and then because the second one is just a multiple of the first, I'm just going to get here. And so this implies that we get that 5x1 is equal to 3x2, which of course is x1 is equal to 3/5 x2. And so from this point, this implies that our equilibrium vector Q is just going to be 3/5 x2 and x2, or in other words, we're going to get x2 times 3/5 and 1. And at this point, you might be looking at this thing and going, well, this isn't a probability vector at all. And I would say, yes, I totally agree with you, right? Because this column adds up to be larger than 1. And so how could you scale everything so that the total components just add up to 1? The way that you do that, you would just end up dividing everything by the total value of what's in the column, kind of like averaging, right? So for instance, if I gave you a column that had like 3, 4, right, then, and if I wanted to just scale this in such a way that the components added up to 1, I would say, oh, the total is 7, so I'm just going to divide the top and the bottom by 7. And all of a sudden, now I have a probability vector that makes a lot more sense. So here, because in this particular example, we've solved it and said, oh, our steady state vector here is 3/5 and 1. But because those add up to 8/5, what we're going to do is we're going to divide 3/5 by 8/5, and so this implies that our steady state vector, once I divide 3/5 by 8/5, I'm going to get 3/8 in the top, and then if I divide 1 by 8/5, I'm going to get 5/8 in the bottom. And I claim, that this, by the way, if you want to put this in decimals, is 0.375, and this is 0.625. And so what this means is that, based on this probability distribution network that we have kind of come up with here, it says that in the long run, supposing that we actually something that's much more interesting is it doesn't really matter that we started with 60% of the people in the city and 40% of people in the suburbs, kind of irregardless of that, just based on this. If you started with less than the equilibrium or more than the equilibrium, if you've taken differential equations, you'll kind of get where I'm getting at. No matter kind of where you start, as long as you don't start at 0, eventually you're going to trend towards this steady state vector. You're going to trend towards this population distribution. So in other words, we would expect that 37.5% of the population ends up in the city and 62.5% ends up in the suburbs. And if you want, you should definitely never believe anything that I say. You should check this and make sure that it is indeed the steady state vector for this particular matrix, and that it works by simply just completing the eigenvector equation. So just do the multiplication and make sure that you get out what you put in. And yeah, that's going to do it. That's Markov chains. It's a very interesting application. The textbook has a bunch of examples. So if you head over to 5.9 in the textbook, there's a bazillion examples on it. There's going to be a few questions on it on your homework. But that's going to do it. This is the end of the material for this linear algebra course. So congratulate yourself on making it this far. If you're still mildly lucid, then that in and of itself is a victory. So you work on the homework, finish the homework. Prepping for the final is going to be something as simple as just going through the old homeworks. I would say run through the quizzes. If you feel comfortable with those, you feel comfortable with the true and false questions, you're going to feel really comfortable with the final. And there's nothing that's going to really come out of left field. So the final is going to be in the same way as the quizzes. You have 24 hours to do it. Submit on Canvas, the same whole shtick. So that's going to be it. So as always, post any lingering questions you have in the discussion, or email me some, or maybe reach out to the ether that is Stack Exchange on the internet and ask some questions there. Do your studying and then just prep for the final. So congratulations, and that's it.